sorry, I was trying to get the video started, so we've got it ready to go. So we're taking new notes today. We don't need to talk about people's shoe size anymore, thank you. It says, what are the characteristics of exponential functions? So you guys are used to having linear functions. Linear means when you graph it, it looks like a straight line. It's proportional. You usually have a constant rate, which means you're not speeding up, slowing down, stuff like that. When you have an exponential function, that means in your equation, you have an exponent. So the first thing that you guys see right here is you have this equation, f of x equals 2 to the x power. So then it gives us this table right here. I'm actually going to try to make this bigger because see if it will work that way. It gives us this table and it tells us what numbers to plug in. So this is why exponent rules are super important here, because now we're going to start getting exponents in our equations. So if I want to plug in, it would be like having 2 to the negative second power, which we just talked about how we don't want to have negative exponents. So that would turn into 1 over 2 to the second power. And we know what 2 to the second power is. What is that? 4. So this is the same thing as 1/4. So when you plug in -2 for x, and you can see x is an exponent this time, we actually do have to simplify it because we know our exponent rules. And when we have x to the negative first power, it would be 2 to the negative first. I don't know why I said x. That would become 1 over 2 to the first power, and we know 2 to the first power is just 2. So the second one for -1 is 1/2. The next one we would do is 2 to the 0 power, and this is another exponent rule. It's been a long time since we've talked about them, but anything to the 0 power is 1. The next one would be 2 to the first power. So what is 2 to the first power? 2. 2 to the second power is the next one, which is 4. And then 2 to the third power. Yeah, that'd be 2 times 2 times 2, which is 8. So we're just filling them out here. These right here, I'm just circling them. Those are the actual answers that we're interested in. I showed my work there, but those that I circled, those are our answers. So in the blank, it says the functions get closer and closer to the x-axis, but they never quite reach it. When a function approaches a line in this manner, the line is called an asymptote. So ASYM, I'm bad at spelling. I would have spelled that completely wrong. Yeah. So basically an asymptote is where it gets really, really, really close to a line but never touches it. So if you look here, it kind of looks like it's sitting on the x-axis, but it's just going to keep getting smaller and smaller and smaller fractions as you go negative. It's never actually going to get to 0. So if you tried x to the negative, or if you tried to do x is -3, you'd have 2 to the negative third power, which would turn into 1/8. So like I said, the more negative numbers you use, 2 to the negative fourth, that would be 1 over 2 to the fourth. And so you're never actually getting to 0. You're just getting smaller and smaller and smaller and smaller fractions. That's called an asymptote. Okay. So it says key features in this graph. So this is talking about the graph that we just had right here. So the key features of this graph is the y-intercept is 1. That's where my line crosses the y-axis. And you can see right here, it actually tells you the point that it crosses at 0, 1. So that's the y-intercept. The asymptote is y equals 0. That's also known as the x-axis. Domain. So those are the different values the different values you can use for x. So what kind of values can I plug in for this little x right here? Is there any restriction at all that I can use? So if there's no restriction, the domain is all real numbers. I can use any real number that we know. And you're probably like, why am I talking about real numbers? There is such thing as imaginary numbers. You'll talk about that in Algebra 2. Not right now. An easier way to write all real numbers just for future references, you'll have 2 lines and then you'll draw an R. That means all real numbers. So instead of having to write it out every time, you can do that instead. And then they want to know what kind of y's are you going to have. So domain is your x values and range is your y values. So if we go back and look, what kind of y values are we getting? Remember, it never hits this 0 point. They're all going to be greater than 0. So in the range, we're going to say y is greater than 0. And the reason for that was we never got 0. We just kept getting smaller and smaller and smaller fractions. So we know that they're all going to be greater than 0. I don't know what it means by work. We don't have any work to show. So we're going to move on. Okay, so this is a word problem. It says a network administrator uses the function f of x equals 5 to the x power to model the number of computers that a virus spreads to after 8x hours. If there were 1,000 computers on the network, about how many hours would it take for the virus to spread to the entire network? So then this is like a graphic explaining, okay, one computer gets a virus, then it gives that virus to 5 other computers, which gives that virus to 5 more computers, and you get the deal. Like, anyway, this is a really interesting thing right now because of COVID. COVID is definitely an exponential function. Does that make any sense? Like, if you get it and you're surrounded by people, and you're giving it out to those people. If those people are surrounded by people, then they're giving it out to those people. Do you know what I mean? This is an exponential function. It's a great example of one that is happening in our real life right now. So there's someone who's doing a bunch of research right now about that, and they're using math. We have to make a table. So remember the equation that we're using is f of x, and it's right there. I'm just writing it bigger, equals 5 to the x power. So if I want 0, it would be like I'm taking 5 to the 0 power. That represents if no computers, well, anything to the 0 power is what? What? 5 to the first power is 5. 5 to the second power. 5 to the third power. So remember, we're taking 5 times 5 times 5. The next one would be 5 times 5 times 5 times 5. There's an easy way to type that in your calculator. Did I show you yesterday? Okay, so you can use that. 5 to the fourth power, 625, and 5 to the fifth. Okay, so a lot of people think that that is taking 5 times 4, taking 5 times 5, but let's make sure we know what we're doing. If I want 5 to the fifth power, here's my calculator. Here's my 5. I don't know, for whatever reason we can't see things today. 5 caret 5, that is 5 to the fifth power. It's also the same thing as taking 5 times 5 times 5 times 5 times 5, but I don't want to type that in every single time, so I use the exponent button in the calculator. Okay, moving on. And they give us this graph. They've already graphed everything for you. They graphed 0, 1, 1, 5, 2, 25. And then they give us this little box here, and after here, it says after 4 hours of the virus. I'm going to try to fit this in here. After 4 hours of the virus, so go to 4 and go see where it's about 10 or 1,000 computers are affected at this point. So the difference between a normal equation, like a linear equation that we've done in the past, and the exponential equations is that exponentially grows very quickly, very fast. So like just the difference from 0 to 4 is 1,000 basically. So in a linear equation, it's going up by the same rate every single time. That is not the case in this kind of graph, which is why you're going to get a curve to your graph. It's going to get bigger very quickly. The last thing says about how long did you estimate it to take? What am I? Oh, I guess we have a question at the top. It says, how many computers will it take for the virus to spread to the entire network? Okay, so their network is 1,000 computers. Well, how long did we just figure out would get to 1,000 computers? So that's your answer to number 1, 4 hours. It's in between 4 and 5 hours. So you see how big that jump is right there? We can put a little more than 4 hours, or between 4 hours and 5 hours. Use a calculator to check the accuracy of your estimate. So make an estimate right now and pick. Like I heard someone say 4.5. Make an estimate right now. Pick what you think. I know it's between 4 and 5. But if you look at 4, 4 was 625. If you look at 5, 5 was 3,000. And we're trying to get to 1,000. So someone tell me what your prediction was. 4.15, 4. So then if you're trying to check that, you're going to take 5 and you're going to raise it to that power. So if I chose 4.15, I'm going to get my calculator, type in a 5, and then caret 4.15. That's like almost 800. That's 795.6. So whatever if you did like, I just heard 4.3, you would take 5 and you'd raise it to the 4.3 power, which is 1,012, which is pretty close. And then it wants to know, what does your answer mean? That just means add around, and then you use your prediction number. So if you use 4.3, you'd write 4.3. If you use 4.15, so I'll just use 4.3. At around 4.3 hours, 1,012 computers were affected. Okay. Moving on. Okay, so the first blank, it's an exponential function. I'm going to try my best to write this nice and neat. Exponential function. It's a product of an initial amount and a constant ratio raised to a power. So this one right here is constant ratio. Exponential functions are modeled using f of x equals a times b to the x power. Things to remember about a is it cannot be 0. Things to remember about b has to be greater than 0, and it can't be 1. So we're going to look at a table now. This is a table of an exponential function right here. And it says, what is the written form of the function of this table? So what we're going to do is we're going to look at these numbers right here, and we're going to divide. So what is 12 divided by 4? What is 36 divided by 12? What's 108 divided by 36? Logic would tell us we're looking for 3's, but yeah. And the same thing, 324 divided by 108 is the same thing, 3. So it says, what is the initial value? So when x is 0, what's the first number that we have? When x is 0, what's the number that it gives us? 4. So our initial value is 4. What's the constant ratio, or the thing that we kept getting when we divided? 3. Okay, so now we're going to write our rule, for our equation for this table. So you always start with f of x. That just means you're working with a function. A is the initial value, and we just came up with our initial value, which is 4. Our constant ratio is 3, and we're raising that to the x power. We don't know what power we're wanting to raise it to yet. We're just trying to come up with a formula that would work for whatever number we wanted to plug into that. So that is how you do the table right there. The next one they give you is a graph. So it says, what is the written form of the function of this graph? So what you want to do for your initial value, look and see when x is 0, what is your y? And I'm pretty sure there's supposed to be a 1 right there because that one's 96. So we're going to say the initial value is 128. The constant ratio, so what we're going to start looking at is, how do I get from 128 to 64? What do I have to do? Divide by 2. How do I get from 64 to 32? Divide by 2, 30. Yeah. The next one is not on here. They go from 2 to 4, but what's 32 divided by 2? That's what this missing one would be. 16 divided by 2 is 8, and 8 divided by 2 is 4. So our constant ratio, we know we divided by 2 as a I didn't even see it. Yeah. So where our constant ratio is going to be 1/2. We're dividing by 2. You're taking your y and you want half of it. So now we're going to substitute those numbers in. Our initial value goes first. So we say f of x equals our first number, which was 128. My handwriting is terrible. Times 1/2, and we're raising that to the x power. That's the rule for our graph. Once we figure out our first number and then we figure out how we're getting to our next number, our constant ratio, then you're good to go. So the key here, so we wrote divided by 2. I want to note a couple things. If it looks like you're doing division, you're going to switch it to multiplication. So I knew that dividing by 2 and taking something times 1/2, those are the same thing, but that's how I got this 1/2. So if dividing by 3 and taking something times 1/3, that actually means the same thing, but you're looking for the multiplication part, not the division part. And I know my handwriting is so bad right there. But yeah, you can change it to a fraction, and that would be what you're multiplying by. Okay, this time they don't give you a table, they don't give you a graph, they just give you ordered pairs. So your initial value is the first one. What is your y when x is 0? So here's 0. What was my y? When x is 0, y was 3. What is the constant ratio? So now we're just looking at our y's right now. We are going up by how much? Every single time, times 4, times 4, times 4, times 4. So our constant ratio is 4. Now we're just plugging things in. 3 times 4 to the x. Okay, now they're going to throw in some word problems, and we're going to have to fill in our table. So it says, Felicia is offered 2 pledge options for donating to a charity. Her first option, A, is she'll give $100 the first week, and then each week after that, the amount increases by $25. Then option B, she gives $1 for the first week, and each week after, the amount triples. So let's think about our 2 tables and let's fill them out. In the first one, it's just increasing by $25 every week. So 100 plus 25 is 125. 125 plus 25 is 150. Then you'd have 175 and 200. This one is more of a linear equation because you're increasing the amount the same amount every single time. The other option, this is more of an exponential option because it's tripling the amount every single time. So what is 1 times 3? And what is 3 times 3? What's 9 times 3? What is 27 times 3? And let's do one more just to see. What's 81 times 3? Thank you. We're going to extend both of them to week 5 because that's where you'll see where one option is better than the other. Okay, so the last question for this says, which option will increase the pledge amount faster over time? So if I'm only going to do this for 2 weeks, I would choose option A because I'd make way more money after 2 weeks. But if I'm going to do this for a long period of time, which option would be better? B. So what they wrote in here, in week 4, option A gives more money, but week 5, option B gives more. I'm going to paraphrase that. Week 4, option A. But week 5, we would definitely want to go with B. Week 6, yeah, I mean, I guess we're in the view of the company. Like, if we were the company. This is a very unlikely scenario to begin with. I'll say that. They're not going to give you 2 options. They're just going to have you donate, but whatever. It is what it is. Okay, anyway, option A is a linear function. The option A, the function is f of x equals, we are increasing $25 every week, and we start with an initial value of $100. That's the equation for option A. That's a linear equation. If you were to graph it, it would be a straight line. Every single week, it goes up by the exact same amount. That's a linear equation. Option B is not a linear equation. Option B is a exponential equation. And if you go back and look, our initial value was $1. And then we're multiplying by 3 every time. So it would basically be 1 times 3 to the x power, or just 3 to the x power. And I'm going to go back and show you that really quick. For week 1, it would be 3 to the first power, which is 3. For week 2, it would be 3 to the second power, which is 9. For week 4, 3 to the fourth power, which is 81. So that is an exponential function. That one is going to grow way faster. If I'm that girl, I absolutely don't want to do that. I'm going to be spending so much money by the end of the thing that, yeah, I'm not interested in that.